Hey, YouTube. This is supposed to go a lot faster. Hello? Come on, buddy. You can do it. There it goes. See, it's already at the prompt or whatever. Anyway, if there's one difference between a modern computer and an old school computer like the Commodore 64 that you might have seen me review in a couple of videos, well, it's that the Commodore 64 boots surprisingly quick. I mean, you'd think old computers are slow, right? Older, slower. Newer, faster. You would need a super fast SSD to come even remotely close to how old a computer like the C64 boots. You would need a super fast SSD as a minimum. And then you'd need just other conditions that make your boot faster, like, fast boot with just kind of like hibernation on Windows 10. But, anyway, I'm getting ahead of myself. Why is this the case, anyway? Well, something like the Commodore 64 has a fairly simple boot process. Power is supplied to the computer. When the switch is turned on, the CPU reads the pre-programmed instructions in the ROM to display the basic prompt, interacts with the graphics chip, and a prompt is displayed. If there are peripherals connected, in a very rudimentary way, they're usually initialized, mostly via allocating appropriate memory addresses to them, or executing instructions if it's like a cartridge, for example. Well, what about a modern PC? Well, let's just say it gets a little more complicated there, and this video is an attempt at making some of that complexity a little bit more simple to understand by going through it step by step. For the sake of that simplicity, I will be going over a particular configuration, one that I believe is both common and demonstrates the concepts involved the best. An x86 computer with a legacy BIOS and an MBR partitioned disk with a Linux installation. So first comes power. Computers, they need electricity to run. They tend to be picky like this. And historically, an IBM compatible, or what we know as an x86 computer, would have one power switch in its case, the power supply switch. In the AT standard, which is what those computers used, turning the switch on would cause the power supply to supply the power to the components, and that would be pretty much kind of it. Unlike the AT standard of that era, the modern ATX standard is a little more sophisticated than that. First, there's the switch on your power supply on your desktop ATX computer. While the supply is plugged in and that switch is turned on, the power supply will supply a 5-volt standby power signal at all times. This helps preserve the charge of the CMOS battery, which is better used for supplying power for other things. Side note, the behavior for whether the hard power switch of the power supply actually turns off this 5-volt standby, or whether you have to unplug it from the master outlet, or if the only way to turn it off is to physically unplug the power supply, isn't directly publicly documented by power supply manufacturers in any form yours truly could find. So as far as I understand, it's not a hard requirement for the standard. So when the power button on the PC is pressed, it is a simple switch that connects and then disconnects 2 pins on your motherboard. If they are directly exposed, you can also short these pins yourself with a paperclip, or hook up your own switch to it for convenience or testing. What this does is send the power signal to the power supply by connecting the 5-volt standby power that your power supply is already supplying to the motherboard to a different pin on your power supply. After the power on signal is sent, the power supply properly kicks into action, gearing up to supply the full needed power to the motherboard and components, but it's not directly connected yet. The power supply then will respond to the motherboard by sending a power ready signal. The signal will be activated by circuitry on the power supply's own motherboard, or some sort of controlling circuitry, some type of logic, which will measure the various components inside. in particular the state. This is important because computers require pretty stable power to be able to function properly, and power supply units house capacitors that store a good deal of energy and take a while to charge up. The motherboard will patiently wait for this to happen before continuing the boot process. Realistically, this should take approximately 500 to 1000 milliseconds. Pretty fast. A power button or a paperclip to the pins is also not the only way to start that process. Many motherboards, especially designed for business use, also support booting from their Ethernet adapter, the humble wired network connector. Using the 5V standby power, it is able to wait for a specific packet to come in over the network and initiate the power on process. Damn useful for remote servers no one has any physical access to. Just send a specific packet to them and they turn on. Much more rarely, USB and FireWire devices can also boot computers in a similar fashion. And thanks to the humble old CMOS battery, the real-time clock on your computer that is always going on regardless of any other power sources connected to it, will also let you set a time for your computer to start. So as long as you have your power supply and your CMOS batteries ready, you can usually set a timer. Or at least you used to be able to. I don't see that function much in consumer BIOSes, the kinds that I would interact with day to day anymore, but I do remember seeing it. So if you've seen it, let me know. Anyway, once the motherboard gets the power ready signal, it will allow the supply of power to all the computer's components, the CPU, the RAM, the chipset, and all the peripherals. The first thing the CPU does is load a small program called a BIOS. You might have heard of it. The BIOS ROM, or Basic Input-Output System, read-only memory, is stored on an EEPROM chip. That's EEPROM. EEPROM stands for Electrically Erasable Programmable Read-Only Memory, which means it's memory that can only be read, not written to, and a manipulation of electricity, usually a negative pulse, can be used to erase its contents. If this memory can only be read, how does removing a CMOS battery erase the BIOS settings? I hear no one ask. Well, it's not exactly read-only. As anyone who might have performed a BIOS update might know, in reality it's non-modifiable, meaning it can only be erased and written over, such as is done during the BIOS upgrade. Besides, BIOS configuration isn't stored in the BIOS. In the olden days, BIOS configuration was really stored in volatile memory. Memory, the contents of which rely on power being present. Like RAM, the fact the BIOS was stored in a kind of RAM, SRAM, static random access memory, as opposed to the thing we think of as RAM traditionally, DRAM, or dynamic random access memory. Nowadays, BIOS configuration data is usually stored on a normal non-volatile flash chip, known as NVRAM, non-volatile RAM, named to be quite to the point. The reason why BIOS settings are reset when you actually pull out the CMOS battery is because some designer somewhere decided that simulating this old school behavior is a good thing, which I can see why. Users will have an expectation of what that does, what it historically has done. Since there's no direct correlation to it anymore, most modern motherboards like my X370, Ryzen motherboard names are really memorable. X370 motherboard here will actually have a dedicated way for resetting this data by shorting 2 jumper pins on the motherboard with any metal object of your liking. This will erase the data contained on the flash chip. This isn't some hidden knowledge, it's directly stated in the manual as the quote-unquote right way of doing it. I do think a poor implementation of this could lead to making BIOS passwords useless, as they could just be erased along with any other configuration data, which is pretty laughable and ridiculous from a security standpoint, almost as bad as the backdoor passwords some manufacturers build into their motherboards. Yes, that's a thing. At the very least, if your laptop or server or desktop is equipped with a Trusted Platform Module or TPM or something similar, usually while removing the CMOS battery might still reset the specific configuration settings, the BIOS password will be stored in the TPM. Thank God, also Lenovo, which makes ThinkPads, I don't know if you know this, does not have any backdoor codes, not that I'm aware of anyway. They could as well just be not publicly disclosing that information, which is good. But anyway, it also ships a trusted platform module with ThinkPad, so ideally the point should be moved. Removing the CMOS battery will still clear the date and time though, as the real-time clock, being a constantly running oscillator, does require power to work and is always on regardless of the state of the system otherwise. But I digress. Talking about BIOSes for way too long. Maybe I'll cut this part out, or maybe not. But I digress. Why is it so important to keep the BIOS secure anyway? Well, this program interacts with hardware on a very low level. It has access to everything, and it needs to. During the boot process, the first job of the BIOS is to perform a POST, a power-on self-test, which will test that all the components of your computer are functioning properly, in at least a rudimentary enough way to continue with the boot process. In an x86 system, the main functions of a POST is to verify the CPU exists. This isn't really a check that the BIOS performs, as the CPU is usually needed to execute the BIOS code. And remember, BIOS is really just a program, basic input-output system, making sure the CPU works in some rudimentary way. Things like the lack of a CPU, broken CPU, or an incompatible CPU would fail this check, as the CPU will never ask the Northbridge chip of the chipset for instructions, which is how the BIOS program is usually executed, and thus BIOS will never be executed. And this is why you can't update your first-gen Ryzen, AMD Ryzen CPU's board BIOS with a Ryzen 2 CPU, for example. It won't get very far at all into the boot process, not even into the BIOS itself. What is there to execute it? Anyway, unless you've got one of those fancy boards that have essentially a whole other processor that will allow you to specifically flash a BIOS version even without any CPU in the socket at all. Once the BIOS is executed, providing a CPU is present, it usually verifies the CPU again by executing an instruction and comparing its output with an expected output stored in the BIOS to make sure the CPU also works properly. The operation is usually rather simple and rudimentary, usually involving something like a bitwise shift on all the CPU's registers. A bitwise shift is an operation that's too complicated to get into in the scope of this already massively bloated video. The next big test is the exception and interrupt test, usually carried out by deliberately creating exception conditions, such as dividing by 0 and seeing whether the CPU handles this and seeing whether the appropriate handler has the control handed over to it. Interrupt tests will similarly see whether an interrupt handler is utilized. Next, it will usually test memory. Now, how the BIOS does this is wildly up to the manufacturer. Some old IBM BIOSes did it through a memory test, equivalent of running memtest, but today that's not very practical. Testing 16 megabytes of memory is quite a bit less of a task than testing all 32 gigabytes of a high-end modern desktop, so this test is usually rudimentary and only tests for basic faults like data line faults and address faults, which would hint at electrical failure within the memory slot or the RAM stick itself or whatever RAM chips, and not specifically that your RAM's working perfectly fine. Which is why if you have like completely messed up RAM or you somehow managed to insert it the wrong way in and you didn't notice, like yours truly did once, growing pains of learning how to build desktop PCs, well, yeah, that can happen. It just won't boot at all. Anyway. Next up, the BIOS usually checks the integrity of the code of the remainder of the BIOS. Not all of it is loaded at this point, and things like the configuration utility that lets users configure various aspects of their computer, such as a set of preferred boot drive or whatever, need to be verified as actually being that before they're run. Post power on startup test will also test a variety of things like dedicated memory addresses and the system timer, It will also initialize and pass over control to other BIOSes. This could be I/O controllers like RAID controller card, for example. It will also initialize the VBIOS or the video BIOS, which is usually how a graphics card, GPU, will initialize itself with its own small embedded processor doing that work. During this, the computer will usually have some mechanism for reporting errors. What that mechanism is varies massively between manufacturers, and they usually use some combination of beeps, LEDs, diagnostic error codes displayed on the motherboard, or display connected to the computer. Non-x86 computers also had a variety of beep codes. Let's talk about them, as if this video doesn't have enough tangents already. Amigas had colors of the rainbow it would fill the screen with during the startup that could either indicate normal boot or startup failure. Macs had a sad Mac icon instead of a happy meal, happy Mac, along with hex codes displayed on the screen and a chime of death, sometimes being an aggressive arpeggio. Classy, huh? Well, anyway, modern PowerPC Macs like this thing that looks like it's one of those, your brain on drugs graphics in an anti-drug PSA right here, the iMac G3, usually had startup tones. Until being revised again in 1999, before being revised again when Mac switched over to our boy Intel x86 and started using relatively standard EFI firmware, until of course that changed again with the T2 security chip, and it changed the boot process entirely and removed all the tones as far as I'm aware. But this isn't just Macs being special, really. The post codes on my ThinkPad 380XD have absolutely nothing to do with other laptops or desktops, but even other ThinkPads made by IBM had different startup codes and error codes. Great. Sure, there are some commonalities. On the CompTIA A+ certification exam, an entry-level computer technician competency qualification that is vendor neutral, describes post codes as combinations of long, short, and continuous beeps. But if that's your sole source of knowledge of that, ironically, you wouldn't even be able to troubleshoot a consumer board at home these days, especially with the gaming boards and stuff with their fancy codes and little startup lights to help you out. It's unlikely they'll have a PC speaker through which to emit these beeps through, and like my X370 here, they'll use LEDs. Luckily, they're described in the manual, though those neat full code displays are nice, not to talk of those nice sweet post-diagnostic cards that show you the progress of the boot. Once that's done, at the same time as loading the configuration utility, the later stage of the BIOS will usually do a number of tests, depending on the configuration, like discovering, initializing, and cataloging all the system buses like the USB bus and the PCIe bus and devices. Some BIOS programs are very, very basic and simple. The original IBM PC BIOS was contained in a small 8 KB, that's 8,192 bytes for the uninitiated. Some don't often have a lot of settings and menus to navigate through to configure the program, and so have a ROM size of 256 kilobytes, and some others like my trusty ThinkPad X201 here have an 8 megabyte BIOS. I'm looking at you, gaming motherboards, other motherboards, and I'm looking at you here, gaming motherboards have a 16 megabyte monstrosity with gamer graphics in every setting under the weather. Some motherboards even have a whole tiny Linux distribution packed right into the BIOS ROM chip, though usually at that point we're talking about UEFI. Harkening sort of to the good old days in a way, if you think about it, where 8-bit computers and the basic routines and their associated prompt was stored entirely in ROM. Here you don't need a drive at all to use the small Linux distribution packed into the ROM of your computer. Even to x86, this actually isn't a totally new concept. Microsoft, in fact, offered a version of MS-DOS that would sit on the ROM of the computer itself, instead of how you would usually boot MS-DOS, which was via a boot floppy. That way, you didn't need to buy a separate boot floppy, and your computer wouldn't become a paperweight if you lost or damaged said floppy. One last function of the BIOS is to find a bootable device, either via a predetermined order or via a specific user-configured order. That boot device can be anything, whatever the computer supports booting from, like a floppy drive, a CD-ROM, a hard disk, or a USB stick. These are limitations based on the BIOS-specific implementation, and the chipset, and the CPU, and all those other things. A lot of computers still to this day won't boot from things like USB 3, PCIe expansion cards. When partitioned under MBR, which is master boot record, as is in this discussion, a master boot record specifically is the first 512 bytes of a disk, and those are present on each drive. This boot record will contain a special area known as a boot sector, usually at byte 0, addressed by a logical block address 0 in an LBA system, or cylinder 0, head 0, sector 1 in a CHS system, cylinder head sector. When the MBR finds a valid boot sector, it determines the drive as bootable and hands off the execution to it. Before it does this though, there's one final step that's preparing the environment. This widely differs between configurations. Generally speaking, the boot sector code, known as bootstrap code, is loaded into a physical address at 0x7C00, and the CPU is put into real mode. Real mode was originally the only mode that x86 processors could operate in. It's 16-bit with less than 1 megabyte of RAM accessible. For backwards compatibility, all x86 processors start out the execution in real mode, while operating systems generally run in protected mode, offering memory protection and being able to address more memory. When a drive is partitioned in NTFS and FAT32 and exFAT partitions, there is usually also a VBR, a volume boot record, specific to that partition. The partition table specifies which partition is active via a special active flag. If it's 00 hexadecimal, then it's not active, thus not bootable. When it's set to 80 hexadecimal, or 80 rather, it is considered bootable. When the MBR code does is prepare the environment for the OS specific bootloader and find this partition and jump the code execution to it, where a jump JMP instruction at offset 0 of that partition will go to the execution of its bootstrap code, which will usually serve as the first stage bootloader. In Linux, this is usually grub first stage. Alternatively though, the first stage bootloader may be installed directly on the MBR itself, instead of being told to jump from MBR to the VBR boot code. It will go directly to a specific location containing the bootloader. On Linux, the MBR bootstrap code may be the first stage of grub, which will load the second stage of grub directly off the /boot partition or the /boot directory on the main drive. But let's be more specific. The grub2 bootloader, which is the one that's used on most common Linux distribution these days, really has 3 steps: boot.img, core.img, and whatever's contained in the /boot/grub directory. One way to boot would be to have boot.img in the bootstrap code within the first 512 bytes of the MBR, but as that is very little, approximately only 440 bytes actually usable, to hack around this, it will use a gap just after the MBR and before any other data begins, known as the DOS compatibility region, which gives approximately 32 kilobytes more usable space for the first stage of the bootloader. Though in reality, this is more like step 2, sometimes referred to as stage 1.5. Sorry if this is getting a little bit messy. Still with me anyway. In this area, core.img would be stored in the 32 kilobytes. This can do a lot more than our initial file, because that initial file had to fit into that small master boot record region. This will usually address the /boot partition or the /boot directory by path. How it can do that is via software. If the /boot is a separate partition, due to encrypted root and or home partitions, core.img will address that boot partition and continue the boot process, usually via something like HD0, 2, which will be the address for the secondary primary partition on the first hard disk or whatever our boot device is. Since MBR supports a maximum of 4 physical partitions, and Grub at that point has no way to deal with logical volumes, the big limitation is that the remainder of the bootloader must be located on a physical partition. The reason core.img exists at all is because there is not enough space in boot.img to contain various file system drivers such as NTFS, FAT32, exFAT, and ext4. The /boot partition or directory has to be located on a supported file system for the process to continue. And the reason for loading all these drivers is to be able to support a wide variety of configurations and thus be able to continue the boot process. From there on, all of Grub has been loaded and will now perform its function. What is its function? Great question. It'll do 3 main things: list the available kernels, which it will usually find in the /boot partition, use the MBR partition table as well to detect any other operating systems that may be present on different drives. Second, present a user interface, both in command line and graphical form these days, that allows the user to specify particular boot options and choose what kernel or operating system to boot into, and then hand off the control to that. Usually when talking about kernel, we mean like Linux kernel, and we're talking about a different operating system, as in the context of booting from Grub, we're usually talking about Windows, with its own bootloader like Boot Manager or NT Loader, I think it's called, for the new Windows operating systems, and allowing it to handle things from there as if the system natively booted into that. Since Boot Manager doesn't support booting into Linux, it's usually advised to boot into Grub, the Linux bootloader, and then boot into Windows from that. What it will do is revert the system peripherals, such as putting the system in protected mode, etc., to just let Windows do all of that itself, let it have it. The Grub menu, the graphical interface I mentioned earlier, will either load a default or present the choice to the user depending on underlying configuration. It may do a bit of both with a little timeout, loading default in 10 seconds. When it comes to the Linux kernel, once it is selected by the user, Grub will hand off control to it, and that will then continue the boot process. Other than loading the Linux kernel, it has one last feature. initrd will also be loaded. initrd is initial RAM disk. Initial RAM disk. initrd, not IRD. But whatever. It is loaded and mounted as a substitute for the real root file system, which will be mounted later. Like, for example, when cryptographic decryption devices are loaded and the user can enter a password for their encrypted root partition. Its functions are to serve as a bridge to the gap and allow for operations very early in the kernel boot process. It will contain some executables and some drivers that will let the kernel do things like allowing it to install kernel modules and also mount the root file system after running an initializer program from it, like init. Once the real actual root file system is mounted, the initial RAM disk file system, or init RAM-fs, is unmounted. However, on embedded systems, init RAM-fs may actually be the only root file system that there is. Crazy, right? Anyway, to save space, the Linux kernel itself is usually in a self-extracting archive. When execution is handed over to it, it will extract and decompress itself first. And once that's complete, it will perform a number of tasks, usually reconfiguring devices more appropriate specifically to itself. Map out those devices and get their info, as identifying information reported by a USB device, like its manufacturer ID, memory for PCI devices, initialize how much graphics memory is available, implement things like spectrum mitigations, generate enough randomness for the rest of the process, like establishing Wi-Fi networks, negotiating things, and it does a lot of stuff, right? Isn't that the point of this video? There's a lot of stuff. Arguably, the most important of that stuff is to run systemd or init, Which one usually depends on whether your Linux installation is systemd based or can be described with the name of this channel. Systemd still does basically at its core what init always did: initialize the system, doing operations such as mounting file systems, setting up swap files, starting udev, setting the random generator seed, initiating low-level services, setting up cryptographic services, at which point usually you'll enter your LUKS password to decrypt your root and or home partitions. It'll also start services and daemons necessary for other programs to run, such as databases that are required by other applications later in the boot process, or starting the networking service, like I talked about Wi-Fi networks earlier, for interaction with network interfaces such as your Wi-Fi and Ethernet, and eventually starting a login or / display manager like GDM, GNOME Display Manager, or LightDM, Light Display Manager. Honestly, the amount of services and how they all interact is a video on its own. If not a whole Netflix series. But I think it's worth talking about how systemd determines which services are actually needed to boot. You may be familiar with run levels, because it was mentioned in that one Mr. Robot episode, Init 5, that Rami Malek's character Elliot Anderson mentions is a state into which a Linux system can boot. There are init levels 0, S, 1, 2, 3, 5, and 6. 5 means a graphical multi-user mode, meaning multiple users can log in and the system aims to start all of the graphical services, such as the display manager, which in turn will do all the necessary starting of the Xorg graphical server. This is by far the most common run level on a personal computer, while on a server, run level 3 will likely be the most common. At this level, multiple users can log in and have concurrent sessions, but the system never starts graphical run level services, meaning the system will boot to a command line interface login prompt instead. Everything else will run perfectly though. Run level 2 will be the same as run level 3, but without network file systems mounting and allowing access of only local file systems, things that are plugged into your computer. At run level 1, only the most basic services run, along with a rescue shell on the console. Local file systems are still mounted. Did I say fire systems? Jesus, this script is complicated. Please give me a break in the comments. Run level 0 is system shutdown. Run level 6 is system reboot. Run level S serves the same purpose as run level 1, sort of being like the rescue run level, except in this case no file systems are mounted at all, and this system is completely in single user mode, hence the S, with no services running. S could also be Superman because you're trying to rescue the system. I'm not sure if that's a correct interpretation. Let me know in the comments. In case you're wondering though, I'm sure you are dying with curiosity to ask me, no, there is no run level 4, but you can make one. In a similar way, you can alter any of these. Systemd actually doesn't really have any run levels anymore. That is init terminology, hence why they're referred sometimes as init 5 and so on. Instead, systemd has targets which specify what and how the services are ran for each run level or target. And you can change it to your heart's content. Just beware that doing so can have very bad consequences. Also, the exact definition of run levels, usually by default, depends on the Linux distribution. Gentoo, Slackware, and Debian, for example, 3 common and famous Linux distributions, all have slightly different run level definitions. Systemd will actually match those run levels with appropriate targets. If our desired systemd target or init run level have been achieved, all the services necessary should be running from then on. Either a graphical or CLI environment is presented to the user, from which they can now do productive things with their computer, like watch this video. Yeah, wow. From pressing a button to finding your favorite internet video to watch, which should be this one. I worked really hard on it. If it's not, I will come to your house and I will kill you. It only makes you appreciate just how complex operations that a computer performs and just how quickly it actually manages to do them. But to answer my question at the beginning, why do modern computers boot much more slowly? Well, we just kind of did, because they do a lot more stuff. If they don't do this stuff, they don't work. The stuff has allowed us to perform many more things with our computers than before. Support operating systems that can support multiple configurations, different hardware, different software components, and serve every human need. Those computers are trying really hard, and well, who's really trying hard is the engineers behind them. So next time your computer boots a little bit slowly and you kick the damn old thing, or you throw it off into the video for a funny YouTube sketch, just keep in mind that someone worked really hard to make sure it boots as quickly as possible while also supporting a ton of different configurations and user needs. Wow, this was quite the video to film. This was quite the long video to film. This is the first time I actually spoke directly to camera. I'm pretty anxious about this. I'm not the kind of type that really likes to see myself on video too much, but I think that this might be enjoyable. Get to build a connection with you, the audience, and me, the presenter. And of course, this video, if there's anything wrong with it, if there's any mistakes, you should let me know. You should put it in the comments below so that others can see it as well. I've never done a topic this massive before. Well, recently I did a topic of similar size, but this required a ton of research. And me being on camera, I wouldn't be surprised if something went wrong. So don't feel shy about pointing it out. Thanks for watching, though. Subscribe, like, share, and comment your suggestions and corrections below. If you're still awake, that is. I know that people go to sleep to videos, and that's alright. If that's the case, good night. So, yeah, thanks for watching again, and don't forget to click subscribe, and don't forget to check out some of my other videos. Some of the ones I posted recently haven't been getting too many views, and I mean, that's alright if people just don't like them, but do check them out if they sound interesting, and click like on this video if you like what you saw, and if you didn't like it, then don't. Or click dislike or whatever. And don't forget to check out my Instagram and stuff. See ya.